Now, coming to the aspect of what is the shape of that black hole mass. Of course, we have already shown it as spherical, and is it really spherical? Manthan model will contest that, and we'll say that it's not possible to be spherical, and we will also suggest an alternate model for that. Now, let us assume that what classical model is saying is right, that black hole are spherical in nature. The mass of the black hole is spherical in nature. If it were spherical, let us assume this is the black hole. Let us assume this is that spherical mass that we just discussed. And this spherical mass is that of the black hole. Now, if that were the case, the mass would be attracted to this black hole from every angle. All parts of the sphere, the mass would be attracted. But we do not see that. We see that there is only an accretion disk. In the elevation, you see this accretion disk, and in top view, you see that accretion disk. It is only a plane. If it were spherical, just the way you see the light, the mass lit up and seen, you would also be seeing all the mass which is falling into the black hole from every side, that will also be lit up. And what you would see is not an accretion disk, you would see an accretion sphere. You would not see an accretion disk or a plane which is going around, but you would see an accretion sphere. So in a sense, what would be a difference between a star or a black hole? When you see in the telescope, the star and black hole would look the same, because what you have as black hole would have all the masses falling onto it and being lit up. So when you look into the telescope, you would see that the star as well as the black hole are looking the same. It's only when you cut through the black hole, which obviously you cannot, but just in case, only then you would know that it has got only a cover and inside is all hollow. So that is why we say that it is not spherical. And this is an actual photograph it's an optical photograph of a black hole. And as you can see, you see clearly a black part in the center. If it was an accretion sphere, all of this would have the same similar kind of light even at the center. The fact that it is not shows that the black hole is not spherical in nature. This picture may be slightly misleading because you see this part, which as though the mass is moving from on the top as well as the bottom, but it's only the effect of black hole on the light being bent. So you have a black hole here, so you have a the discretional accretion disk. So the accretion disk which is in the front is also lit up, and the one which is at the back is also lit up. The one which you see here is the one which you would otherwise not have seen. It is the accretion disk at the back. The light which is coming out of that is bent, and that is why the accretion disk which is moving from here to here is seen as though it is moving from here to here, and the same one is happening at the bottom also. So in a way, this is not the mass actually falling. The mass is falling only through the accretion disk. This one is only a mirage of the accretion disk which is behind the black hole. So let us assume that Manthan does not agree with the model of spherical black hole proposed by a classical model. What is it that Manthan model suggests? What shape would the black hole mass be? So this is the classical model as is said, and this is what Manthan model proposes. It's almost like a donut. Of course, we will not just propose and walk away. We will give you sound reasoning. So let us go through each of the. So let us assume to begin with, this is the star, which is perfectly spherical, and you want to collapse it into a smaller sphere, and that also should be spherical. Just the way this is an exact sphere, the end result also should be an exact sphere. That is possible only when the collapsing force which I am applying at every point has got to be same. As is shown there, every arrow which is towards the center should be equal in magnitude. That only then and only you would end up with a quashed sphere, a quashed star, which again is a sphere. Now, for this collapsing force to be same, what is most important is that the mass distribution should be uniform. And what is the mass distribution in a parent star? This is what a sun would look like, the cross section. The mass distribution is anything but uniform. So when you have a non-uniform distribution, the forces are not the same. So the collapsed part also will be anything but spherical. Now that is one part. That is a proof to show that the collapsed mass is not spherical. But how does it attain the quashing effect? So when you have an unequal mass distribution, you have differing forces. Let us assume there are two differing forces. One, the collapsing force. One is the primary force F1 and another is the secondary force F2. They are massive, both of them are massive in nature, but one is higher than the other one. So possibly, as can be seen, the one which is shown vertically down is bigger and the one which is shown at the side is smaller. That is when it gets squashed to reach a donut-like shape. But one may say that that is okay in theory. In reality, it is not necessarily that the collapsing forces as shown as F1 and F2 are just two types, or for that matter they are that exactly 90 degree. It could be F1, F2, F3, F4, because this is a very dynamic situation. That the mass distribution, there is no theory to it, there is no science to it, and plus it is dynamic, it is changing. So one may say that it may not be a perfect sphere, but it could be an irregular blob. Not a perfect sphere, but it is an irregular blob. Now, what we should consider here is the spin factor. What I mean to say by spin factor, let me explain it this way. Any geometrical sphere that you take, there would be only one center. Center is a point from where every point on the surface of the sphere is at equal distance, a distance of r that we know as radius. If you replace that with a spherical mass, even this also has a one center. But there is a condition to that. Precondition is that the mass that you are considering should be uniform. Every constituent mass of that spherical shape should be equally spaced, equidistant, and should have the same kind of density. Then only you can say that it is uniform. If it is not uniform, what happens to the center? The center gets offset. There will be two centers in that kind of a sphere. One which is geometrical sphere, another which is the center which takes into account the mass distribution also. When there is an offset and when you have these masses, when the collapsing forces are acting on the center, at a distance away from the geometric center, it creates a spin. And whenever there is a spin, there is an axis, major axis formed. And whenever there is a major axis, the mass rotates around that major axis. And this spin regularizes the shape which otherwise would have been an irregular blob, now will be regularized to form a kind of a disc like a donut. Now, you may ask that, agreed there is a spin and it's a galactic spin. Why can't we have a mass of the black hole, a thin paper-like disc rather than a thick disc like a donut? We should understand that we are dealing with black hole here, that the compressive force is far, far immense in nature. the F1, even if it is smaller, it still packs a punch. So it would not allow the thinning of the black hole mass. It would still be thicker. Then we know that we had shown in the structure, there is a hole at the center. If at all we are talking about such immense pressures of a black hole mass, it's almost impossible to have a hole at the center, because the pressure at the center is going to be the most at its peak. So why is it that we are saying there is a hole at the center? Now this is what we are going to explain now. So we have two things to take care of. One is the collapsing force, another is the spin. There for sure is an effect at the center. It could just be a dip, or it could be a through and through hole, or it could be a bigger size hole. But whatever it is, there is an effect, because agreed that the collapsing force is massive, but the spin is also, we are talking about the level of a black hole. The spin of a black hole is astronomical. It may not be able to change the outer perimeter dimension, but it is good enough to create a dent in that center. And that dent, as we say, could just be a dip or a through and through hole or a bigger size hole. So when we have two options, you could either have a barrel or a donut shape. Barrel you receive when you have as an end result when the spin is more than the collapsing force. When the collapsing force is more than the spin, then you have a donut kind of a shape. And why I say not just a dip but a through and through hole. Size can be, how should we say, debatable. It's not a big hole, it could be a small hole, but for sure it's a through and through hole. We will discuss that in a later stage. You see the gamma rays and the X-rays, which are, whenever a black hole feeds or feeds on a star, it usually ends up burping gamma rays and X-rays at the center. It is generally said that it is not because of the mass coming out of the black hole, because nothing can come out of the black hole. It is that just the mass which is falling onto the accretion disk, that is the one which is coming out as a burp. But if you see, if the mass is falling here, why would it come out of this? It would come out only when there is a weakness there, and that is possible only here. This seems to be the weakness. Where the spin, the centrifugal force is pushing the collapsing force, and that is why, and the burp is not just one direction, it is in two directions, both up and down, and that is why we say it is a through and through hole. Debatable, but this is something which is what Manthan is proposing, and this we can use, we can exploit this as a weakness of black hole. If at all you want to send a probe, you know that side on would not be an admissible thing, because you have an accretion disk which is heating up the mass. So maybe this part is where you should send a probe in, because it is the weak point where you could possibly enter a black hole. But only thing you should be mindful of is the oncoming gamma ray train or X-ray train, because that could have crazy consequences. And in all this, what we should immediately that we should take notice of is, generally shapes do not change in universe. It takes millions and billions of years for shapes to form, to change, to make a difference. But in this case, from that stage to this stage, from the collapse of the equilibrium to formation of this force, it all happens simultaneously in a fraction of a second. So it's not that it is taking millions of years to happen, it all happens just like this.